Let's start the second part of the morning session. And we have two speakers. First is Dr. Vivek Datar. And next one got changed, it was Tapon, but now it will be Devashish Majumdar. Because Tapon is having some issues of retrieving his talk from the cloud. So let's, so may I request Vivek Datar to come to the stage. And first there will be felicitation on behalf of the organizers. And so now Vivek, the floor is yours.
Thank you. So let me first of all thank Vikas Sinha for giving me this opportunity. I had otherwise planned to come just on the last day and say something nice about him, but he wrote to me saying that no, there is a slot and why don't you come and give a talk. So I had to quickly prepare something, and it's not probably the best presentation that I have liked, but it's coming from something very quickly. Okay. So I will talk about the neutrino, which is all around us, and say a little bit about how it might provide into the universe. So, there's not too much of an audience, maybe most of you know about this, but nevertheless, it's like there, we go through it. So this is in brief the neutrino biodata, not all properties, but it's one of the electrons, and there are three, it comes in three varieties, the electron type, the muon type, and the tau type. And for each of these, there is of course the charged electron, muon, and the tau electron. Of course, this figure you must have seen many, many times. There is the quark sector, you have 6 entities, and then there's 4 carriers, the immediate bosons, gamma in case of electromagnetic, the C and W for the B, and then gluon. Can you hear me? Oh, sorry, maybe. Okay, there is no mic on me, yeah, so maybe I should speak here. Okay, sorry. So, of course, it has an extremely tiny mass. We know now from experiments on oscillations, from neutrino oscillations, that it does have a mass. And this mass is extremely small, so this is something, it's not zero, as it would be according to the standard model. So we already have physics beyond the standard model. Of course, you can tweak things and get a mass, and there are many ways of doing it. But the mass is something that is, we know only differences in masses. We don't still know the absolute mass scale of the neutrino. The other thing, of course, makes it very hard to detect, and that's because it interacts very feebly with matter. For instance, a 1 GeV neutrino in iron would travel something like 100 million kilometers, and that makes detectors large and makes things big. Of course, it is the second most abundant particle in the universe, about 3/4 of the density in terms of number of particles per unit volume, as compared to the photon, which is the most abundant. Of course, this is the visible part of the universe, which is, we know, about 4 to 5% only. But this is still one of the important components of that, and therefore it makes it imperative that we understand this part. Also, this could hold the key to understanding some of the mysteries in the universe. For example, why does matter dominate the universe, and why, and in a quantitative way. We know that there is CP violation in the strong sector, but that's not enough. And we think that neutrinos may provide a key to that understanding. Okay, so in order to study neutrinos, we need to know what are the various sources of neutrinos. On the Earth, the sun is probably the most abundant source of neutrinos. In fact, it's about the flux of solar neutrinos is of the order of about 60 billion per second per square centimeter. These are low energy neutrinos. They are of the order of a few hundred keV to or 10 to 15 MeV. Then there are nuclear reactors. They are sources of antineutrinos, electron type of antineutrinos, and they in fact were used for the first detection of the neutrino, something which historically was considered to be impossible. In fact, Bethe and Byers had a couple of papers in Nature in 1934, which said that they computed the cross-section from essentially dimensional arguments and concluded that the cross-section is so tiny, 10 to the minus 43, minus 44 square centimeter for MeV neutrinos, that this is essentially undetectable. And experimenters, of course, have their methods, and about 20 years later, Reines and Cohen and other collaborators indeed found the first evidence for the anti-neutrino at a reactor site in the US. Then there are particle accelerators. So when you smash protons against nuclei, you produce many kinds of particles, pions, and then they decay to muons, and then those produce neutrinos. So if you take a pion, for instance, and allow it to decay in flight, then you can produce a beam of muon type of neutrinos, for instance. And these can be studied because you know the source fairly precisely. And these can go up to much higher energies. They can go up to tens of GeV even. And in fact, I think the latest LHC, they have detected the highest energy probably neutrinos, which are man-made. Okay. Then there are the atmospheric neutrinos. These are produced when high-energy cosmic rays, which are essentially protons, but then much fewer number of alpha particles and heavier nuclei, when they interact with the upper atmosphere, they produce pions, and then they decay to muons and so on, and then you get muon type of neutrinos and electron type of neutrinos at the source. These atmospheric neutrinos are roughly, the muon type is roughly 2 times more in number than the electron type of neutrino. Consider neutrino and antineutrino of each type is the same, counting them as the same. Okay. Now these can be studied, and they indeed have been studied, and that has in fact led to a study of neutrino oscillations. And I mean, the paradigm of neutrino oscillation has in fact solved the so-called atmospheric neutrino anomaly, as it has also solved the solar neutrino anomaly. Okay, then there are supernova neutrinos. When stars come to the end of their lives, then they collapse, and in certain types of supernova, for instance, type 2 supernova, you get these electrons combining with protons to produce neutrons, and other reactions as well, in which you produce a large number of neutrinos. And neutrinos, in fact, account for about 99% of the total energy lost in this massive event when a star collapses and becomes a supernova. And these were for the first time detected in 1987. You all know that, the supernova 1987A, which was detected at Kamioka, and which also fetched the Nobel Prize. The geoneutrinos are something that is emitted as a result of beta decays in the chain of uranium, thorium, and potassium-40 mainly. There are other much smaller numbers of radioactive isotopes in nature, but these also contribute to neutrinos coming, although at a very small rate. That rate is of the order of typically 10 to the 6, so you can compare that to 10 to the 6 per square centimeter per second. So these have also been detected, by the way, by detectors like Borexino, Kamland, and so on. And the total heat production in the Earth, these decays actually account for about half of that, 20 terawatts out of 40 terawatts. This could also tell us something about the geology of the planet, and in fact, potassium-40 is an open problem in geology if these can be measured somehow. And finally, there are these cosmic Big Bang neutrinos. You all know about the cosmic, the radiation, the black body radiation that has been measured to great precision by many of the successive generations of satellites. experiments. However, the cosmic Big Bang neutrinos, which should be some of that same order in number, they have not been detected, although we knew that they should be there. And that's because they're extremely low energy. They are of the order of a few hundreds of micro electron volts. And there are only a few cases that people have thought about to detect them, and they are rather difficult to manage. So if somebody has a very bright idea on this, I'm sure this will also fetch a Nobel Prize, detection of cosmic Big Bang neutrinos. Okay, how do you detect neutrinos? Like neutrons, they're electrically uncharged. On the other hand, neutron at least interacts through strong interaction, so you can measure the charged particles that are produced subsequent to a neutron interaction with the nucleus. On the other hand, the neutrino only interacts weakly with matter, and therefore it's much harder to detect. And there are basically two kinds of processes that are involved. One is the so-called charge current process, in which the neutrino transforms to a lepton, and that is what you can detect, apart from other particles that are produced. And of course, the antineutrino produces the corresponding anti-electron, so the charge current event. There is also the neutral current event. So the charge current event is mediated by the W plus and W minus, whereas the neutral current is mediated by the Z0. So that leads to a inelastically scattered neutrino. It could be inelastic, it could also be elastic. And you have to detect the recoiling nucleus and measure its moment energy and so on. Now this process can also occur as one of the amplitudes that contributes to elastic scattering of the neutrino on the electron. So the neutrino on the electron can go through the charge current case, in which a neutrino transforms to an electron, and then the electron transforms to a neutrino. However, you can also have an event where the neutrino just elastically scatters, exchanging as that goes on. And so these two, since two final states are the same, they interfere, and you actually have an amplitude which carries some information about this neutral current process. I should just say that this neutral current process also occurs for other flavors of neutrino. So if for instance the neutrino changes its flavor, that process still contributes. Okay, and just to complete the story about the neutral current interaction, I should point out that it was, although the elastic scattering, the coherent neutrino elastic scattering was a prediction about 74 or so, it was observed only in 2017. So that's another case. Hoyle pointed out in the case of the Higgs boson, this is also something, a prediction which was made almost 40 years before it was finally discovered. And this was discovered at, of all places, at the spallation neutron source in Oak Ridge, the Oak Ridge National Laboratory for spallation neutrons. So this was a kind of parasitic experiment. The interest in the coherent neutrino scattering is, in some situations, you would be able to reduce detector size by almost a factor of 100. Because what happens is that the elastic scattering, the coherent elastic scattering gives you a coherent effect of all the neutrons that are there in the nucleus. So you get an n squared factor. And so if you have something like a 50 neutron number, you get at least that increase. Otherwise it will be just something proportional to 50. So that's the kind of effect which might be useful in certain experiments, and I think it has not been fully exploited. Although there are experiments right now going on in Oak Ridge to actually look at various target nuclei and to quantify these things. Okay, so I come to the historical problem and its solution. So we all know that the sun produces its energy through fusion reactions, and that happened only as a result of Bethe's work earlier. Actually, Eddington was the first one to propose that nuclear reactions should be responsible for producing the heat in the sun, because at that time people thought that maybe it's something else. I mean, there was Lord Kelvin who even said that no, this is produced by some kind of contraction of the sun and so on, but then that would lead to a very short lifetime of the sun that won't give enough time for life to evolve on the earth. So that's when there are the other sources to be looked at, and indeed Eddington pointed this out, but it was really formally written up, including all the reactions possible, by Hans Bethe, who first proposed the CNO chain, the carbon chain, and then later moved to the PP chain. And so, as it turns out, the PP chain is the one which produces the maximum amount of energy in the sun. Interestingly, the PP chain, which is given here, the first reaction in this chain is two protons fusing to form a deuterium, a positron and a neutrino. And Bethe's paper, somehow, one doesn't know what the reason was, maybe this is there somewhere in science history, but he did not include the neutrino. So actually the reaction was unbalanced in terms of electron and so on. But that's how it was. But he got everything else right. And this PP chain, it turned out, produces about 99% of the energy in the sun. So this is the chain of reaction. There are other smaller fraction chains. So this is called actually the PP1 chain. There is a PP2, PP3, PP4 and so on, but they are much smaller fractions. So many of these either reactions or nuclei produce neutrinos. And so this is a spectrum taken from one of Bacall's paper, who was a pioneer in neutrino science. The flux of neutrinos versus neutrino energy. So you can see that the highest flux comes from PP, which is the very first reaction here. And then there is beryllium-7, which decays. It's not shown here, but beryllium-7 decays by electron capture. That produces a couple of lines. The stronger line going to the ground state and the lower energy line going to an excited state, lithium. And then there is the boron-8 neutrinos. Now these neutrinos are all above 1 eV, whereas the boron-8 neutrinos extend all the way up to about 15 eV. And these neutrinos were essentially the ones detected by the very first experiment that measured solar neutrinos. And this Davis experiment is a real classic in neutrino physics. He ran this experiment for something like 25 years, and of course he was credited with the Nobel Prize. He got the Nobel Prize as a result of this fantastic work. And that work essentially looked at boron-8 neutrinos, because although the flux is small, the cross-section for interaction, so the charge for interaction, goes like E squared. Okay? So that's why, although the flux is small, it still is. Of course, there was a question of also thresholds. So the chlorine detector was essentially given somewhere here. There's a threshold, which is just around the beryllium-7 capture line. Okay. Now, what about this CNO chain? So this CNO chain, although proposed by Bethe in his paper in the mid-30s, it was not possible to measure this because of the low rate at which it occurred in the sun. And only very recently has this CNO chain been measured by the Borex-CNO experiment. This is a result which is, I think, a year old or so, year or 2 years old. Okay? And you can see that, of course, the collaboration has done a great job in extracting the CNO, but as you can see, this is the extracted CNO contribution to the neutrino spectrum. And you can see the total spectrum here. I mean, this is anywhere exactly. At best, it is about a factor of 5, and at worst, it is a factor of 100 or so lower than the total spectrum. So, if there is a method of measuring this by some other technique, certainly it is warranted. Check this out. Okay. Now, what is the so-called solar neutrino problem? When Davis measured these neutrinos, he found that he was getting a number which was about a third of what was expected. And this third was as compared to Bacall, who was his collaborator. In fact, Bacall and Davis were the ones who actually proposed to the Brookhaven administration that they do this experiment. And I was told that Haber initially was not in favor of doing this experiment. He said that this is, I mean, you don't know enough about the sun, and so how can this be? I mean, the rates would be 100 times lower, and so this is not an experiment worth supporting. So the way they got him round to change his opinion was apparently that Bacall convinced Haber that this might be a way of getting a fix on the nuclear interaction cross sections at those gamma energies at which these reactions occur in the center of the sun, and that finally did it. And experiment was funded, and they said that this is. So this experiment was done over many, many years, and they found that there is a big gap between what was expected and what was measured. Of course, when these results started coming out in the mid-70s and mid-80s, there was already a controversy because many of the particle theorists said that you can't blame this on the neutrinos. Perhaps we don't know enough about nuclear reactions. Perhaps we don't know enough about the sun. And so, if astrophysics guys can get it right to within a factor of 10, they should be happy. Why are you worried about a factor of 3? So anyway, Bacall persisted and improved his calculation. So from the earlier errors in some sectors of 30-40%, this got reduced. Of course, as a result of also experiments done in Caltech elsewhere, these got reduced to the level of about 20%. So he was quite confident that there is a problem in the neutrino sector, that this is not because we don't know enough about the sun or that we don't know enough about nuclear reactions in the low energy domain. Later, Kamioka and then also Super Kamiokande did measurements because the thresholds were then low enough that they could measure boron-like neutrinos, and so they measured the flux of these electron type of neutrinos, and they got a number which was roughly half. Okay? So again, there was a problem, and this was again way beyond errors, especially after the Super Kamioka data came out. In fact, the Super Kamioka a few years later came out with a picture of the sun, where you have the resolution is still not good enough because of the angular resolution that is involved there. But in principle, you could get an angular resolution with enough statistics and with enough capability on the photo detection of Cherenkov radiation. You could perhaps get a resolution which is much better. And so you would see the sun actually as in the neutrino sector as a very small object, with only the core contributors. Okay, then there were other radiochemical experiments. So this was a radiochemical experiment. This was a real-time experiment because this looked at classic scattering of neutrinos and electrons. So the SAGE and GALEX did measurements using germanium, and the Russians supplied them with enriched gallium. There were actually 2 experiments, and then they combined, making a combined experiment called GNO. Again, they found an anomaly. Of course, this experiment was the first experiment that had a low enough threshold to be sensitive to PP neutrinos. So this is the first time that we had some evidence that PP neutrinos were actually there, and the PP reaction was first experimental. Okay, and then finally, the Sudbury Neutrino Observatory basically solved the problem of solar neutrinos because it was a brilliant idea put forth in 1984 by Chen, who said that why can't we use deuterium and use the neutral current interaction of neutrinos so that if neutrinos transform to other kinds, such as the mu and the tau type, they would